Section 1. Introduction to Linear Algebra. Linear algebra is a fundamental branch of mathematics. It deals with vectors, vector spaces, and matrices. These tools allow us to represent and solve linear equations. It's a powerful tool for understanding and modeling many real-world phenomena. From computer graphics to machine learning, linear algebra plays a crucial role. Linear algebra provides the framework for understanding data. It also helps us manipulate and interpret data. This makes it essential in fields like data science. It is also used in physics, engineering, and economics. The core concepts of linear algebra are relatively simple, yet incredibly powerful. Think of linear algebra as a language. It's a language for describing relationships between quantities that vary linearly. This means that changes in one quantity are proportional to changes in another. Linear algebra provides the vocabulary and grammar for expressing these relationships. This allows us to analyze them in a systematic way. Linear algebra is essential for any student of mathematics. It also serves as an important tool for those in related fields. Its applications are vast and ever-growing. Mastering the fundamentals of linear algebra opens doors to a deeper understanding of the world around us. Section 2. Understanding vectors. Vectors are fundamental objects in linear algebra. They represent quantities that have both magnitude and direction. Think of a vector as an arrow. Its length represents the magnitude. The direction it points represents the vector's direction. Vectors can be visualized in 2 or 3 dimensions. A simple example of a vector is displacement. Imagine walking 3 blocks east and then 4 blocks north. This movement can be represented by a vector. The vector's magnitude is 5 blocks by the Pythagorean theorem. The direction is northeast. Vectors can represent various physical quantities. These include velocity, force, and acceleration. Vectors are typically represented as ordered lists of numbers. These numbers are called components. For example, the displacement vector mentioned earlier can be represented as 3, 4. The first component represents the eastward displacement. The second component represents the northward displacement. Vectors can be added and subtracted. This makes them useful mathematical objects. This is done component-wise. For example, adding 3, 4, and 1, 2 yields 4, 6. Vectors can also be multiplied by scalars. Scalars are just ordinary numbers. Multiplying 3, 4 by 2 yields 6, 8, which doubles the magnitude but maintains the direction. Section 3. Exploring vector spaces. Vector spaces are collections of vectors. They satisfy certain properties. These properties include closure under addition and scalar multiplication. This means that adding any 2 vectors in the space results in another vector in the same space. The same applies for multiplying a vector by a scalar. A simple example of a vector space is the set of all 2-dimensional vectors. This is often denoted as R squared. Any 2 vectors in R squared can be added together. The result is another vector in R squared. Similarly, any vector in R squared can be multiplied by a scalar. The result is still a vector in R squared. Vector spaces provide a framework for understanding linear combinations of vectors. A linear combination is simply the sum of scalar multiples of vectors. For example, 3 times 1, 2 plus 2 times negative 1, 1 equals 1. 8 is a linear combination of the vectors 1, 2, and negative 1, 1. The concept of vector spaces is fundamental to linear algebra. It provides a structure for working with vectors. It also allows for the generalization of many geometric concepts. Section 4. Matrices and their operations. Matrices are rectangular arrays of numbers. They are fundamental tools in linear algebra. They provide a compact way to represent systems of linear equations. They also represent linear transformations. Matrices can be added, subtracted, and multiplied. Matrix addition and subtraction are performed element-wise. Just like with vectors, you add or subtract corresponding entries. For example, adding a matrix with entries 1, 2, 3, 4 to a matrix with entries 5, 6, 7, 8 yields a matrix with entries 6, 8, 10, 12. Matrix multiplication is a bit more involved. The entry in the ith row and jth column of the product is obtained by taking the dot product of the ith row of the first matrix and the jth column of the second matrix. Matrix multiplication is not commutative. This means that AB is not necessarily equal to BA. The transpose of a matrix is obtained by interchanging rows and columns. The transpose of a matrix A is denoted by A tet. For example, if A equals 1, 2, 3, 4, then A equals 1, 3, 2, 4. Matrices and their operations form the backbone of many linear algebra computations. Section 5. Linear transformations in action. Linear transformations are functions that map vectors to other vectors. They preserve vector addition and scalar multiplication. This means that t of u plus v equals t of u plus t of v and t of cv equals ct of v for any vectors u and v and scalar c. Rotations are a common example of linear transformations. Imagine rotating a vector in the plane by a certain angle. The rotated vector is still a vector. The rotation operation preserves vector addition and scalar multiplication. Other examples of linear transformations include scaling and shearing. Linear transformations can be represented by matrices. This makes matrices a powerful tool for studying linear transformations. The matrix representation of a linear transformation makes it easier to analyze and compute its effects on vectors. Linear transformations are used extensively in computer graphics. They are also used in image processing and other fields. They are essential for understanding how objects are transformed and manipulated in various applications. Section 6. Systems of linear equations. Systems of linear equations involve multiple linear equations. They involve multiple variables. Matrices provide a convenient way to represent and solve these systems. The system of equations can be written as ax equals b, where a is the coefficient matrix, x is the vector of variables, and b is the vector of constants. Gaussian elimination is a common method for solving systems of linear equations. It involves performing row operations on the augmented matrix AB to reduce it to row echelon form. This process makes it easier to find the solutions for the variables. Matrix inverses can also be used to solve systems of linear equations. If A is invertible, then the solution to ax equals b is given by x equals a inverse b. However, not all matrices have inverses. Systems of linear equations arise in various applications. These include circuit analysis, network flow, and economic modeling. Linear algebra provides the tools to efficiently solve these systems. This makes it useful for understanding and analyzing real-world problems. Section 7. Determinants. Unveiling matrix secrets. The determinant of a square matrix is a scalar value. It provides important information about the matrix. It tells us whether the matrix is invertible. It also helps us understand the geometric properties of linear transformations. The determinant of a 2x2 matrix, A, B, C, D, is given by add minus BC. For larger matrices, the determinant can be calculated using various methods. These methods include cofactor expansion and row reduction. If the determinant of a matrix is 0, the matrix is singular. This means it does not have an inverse. If the determinant is non-zero, the matrix is invertible. The determinant plays a crucial role in many areas of linear algebra. These areas include finding eigenvalues and eigenvectors. They also include solving systems of linear equations. Section 8. Eigenvalues and eigenvectors. Eigenvalues and eigenvectors are special values and vectors associated with a square matrix. They provide insights into the matrix's behavior. They are particularly useful in understanding dynamic systems and matrix transformations. An eigenvector of a matrix A is a non-zero vector V. When A is multiplied by V, the result is a scalar multiple of V. This scalar multiple is the eigenvalue lambda associated with V. The equation is AV equals lambda V. Eigenvalues and eigenvectors have many applications in various fields. These fields include physics, engineering, and computer science. They are essential for analyzing the stability of systems. They are also important for understanding the long-term behavior of dynamic processes. Finding eigenvalues and eigenvectors involves solving the characteristic equation det A minus lambda I equals 0, where I is the identity matrix. The solutions for lambda are the eigenvalues. The corresponding eigenvectors can then be found by solving A minus lambda I V equals 0 for V. Section 9. Orthogonality and inner products. Orthogonality is a concept that generalizes the idea of perpendicularity. Two vectors are orthogonal if their inner product is 0. The inner product is a way to measure the angle between two vectors. The inner product of two vectors u and v is denoted by uv. For vectors in Rn, the inner product is calculated as the sum of the products of corresponding components. For example, the inner product of 1, 2, and 3, -1 is 1 times 3 plus 2 times -1 equals 1. Orthogonal vectors have many useful properties. These properties make them important in various applications. These applications include solving systems of linear equations. They also include approximating functions. Orthogonality and inner products are fundamental concepts in linear algebra. They provide tools for understanding the geometry of vector spaces. They are essential for various applications. These include signal processing and data analysis.